A clipboard floats in 3 feet of seawater. The damage control log clipped to it shows 19 separate entries in the torpedo column, each one a timestamp, a location, a compartment designation. The handwriting deteriorates as the list grows longer. By entry 14, the characters are barely legible. By entry 19, someone has stopped writing altogether. The ship is Musashi. The date is October 24th, 1944. The Sibuyan Sea stretches flat and bright around a vessel that was never supposed to die like this. She displaces 72,000 tons fully loaded. Her main battery consists of 9 18-inch guns, the largest ever mounted on a warship. Her armor belt runs 16 inches thick amidships. Japanese naval architects designed her to absorb punishment that would sink any other capital ship afloat, then keep fighting. They built redundancy into every system, triple bottoms, compartmentalized flooding, isolated machinery spaces, counter-flooding tanks that could correct any list within minutes. The theory was elegant. The practice on this particular afternoon has become something else entirely. Below the waterline, in a damage control station that now sits at a 15-degree angle, a lieutenant commander named Katsukiyo Endo watches a gauge that has stopped making sense. The ship has taken hits to port and starboard in almost equal numbers, the kind of distribution that should allow the counter-flooding system to work as designed. You flood compartments on the opposite side to balance the ship. Basic stability engineering. Musashi's designers planned for exactly this scenario, but the gauge keeps climbing, the list keeps growing, and Endo has run out of compartments to flood. We were correcting for torpedoes that had already detonated, one of his surviving subordinates would later write, while new ones were still arriving. That subordinate's account sits in a filing cabinet in the Japanese National Institute for Defense Studies. Most Americans have never read it and assume instead that Musashi sank because American torpedoes were simply better, or because Japanese damage control was incompetent, or because 19 hits would sink anything. None of those assumptions survive contact with the actual engineering. The document reveals something else. Musashi's damage control teams worked the problem correctly. They followed doctrine. They made the right calls. The ship still sank, not because the system failed, but because 19 torpedoes broke the math that the system was built to solve. The distinction matters. Before we go further, drop a comment and tell me how many torpedo hits you think it should take to sink a ship this size. Just a number. Watch to the end. Compare your guess to reality and hit like if the answer surprises you. Subscribe if you want more of these. The American pilots who put those 19 torpedoes into Musashi's hull didn't know they were testing the outer limits of battleship survivability. They were executing attack runs on a target that kept refusing to sink. Wave after wave of TBF Avengers, Grumman torpedo bombers flying off 5 different carriers, dropped their Mark 13 torpedoes into water that should have been lethal for any ship by the 5th or 6th hit. Musashi absorbed the 5th hit, and the 6th, and the 12th. The pilots started wondering if their torpedoes were duds. The air group commanders started wondering if Musashi was somehow immune. Radio chatter from that afternoon includes phrases like, "She won't go down," and "What does it take?" Frustration from aviators who had never seen a target survive this kind of sustained assault. From the Japanese perspective, the view was different. Every torpedo that struck the hull, validated their engineers' predictions. Compartments flooded exactly as the blueprints said they would. Counter-flooding activated exactly as doctrine prescribed. The ship maintained propulsion, maintained communications, maintained enough stability to keep her guns pointed at the sky. For hours, Musashi fought back while absorbing hits that would have sent any other warship to the bottom. The damage control log tells that story in timestamp form. Hit number 1 arrives at 10:27 in the morning. Hit number 11 arrives at 1:44 in the afternoon. 3 hours of continuous attack, and the ship is still making 18 knots. Then something changes. Hit number 12 punches through a section of hull that has already taken stress from 3 previous impacts. The flooding that follows connects 2 compartments that the damage control plan assumes will stay isolated. Suddenly, the counter-flooding math doesn't work anymore. You can't balance a ship when water is flowing between spaces faster than you can pump it out. Lieutenant Commander Endo sees this on his gauges before he understands it conceptually. The numbers are telling him that Musashi has crossed a threshold, that the cumulative damage has exceeded what any counter-flooding system can correct. 7 more torpedoes will hit before the order to abandon ship. Why 19? Why not 5, or 8, or 12? What made Musashi's designers think they could build a ship capable of absorbing this kind of punishment? And why were they almost right? The answer starts in 1934, in a drafting room in Kure, with a naval architect who believed he could solve a problem that Japanese admirals had been arguing about for a decade. The problem was simple to state and nearly impossible to fix. Japan could not outbuild America. The industrial math was hopeless. American shipyards could produce carriers, cruisers, and every other class of vessel faster than Japanese yards could dream of matching. So Japan's architects asked a different question. What if one ship could survive what 3 ships couldn't? Kure Naval Arsenal sits on the inland sea, 30 miles southeast of Hiroshima. In 1934, the drafting rooms here smell like graphite and machine oil, pencil shavings mixing with the industrial haze that drifts up from the dry docks below. The windows stay closed even in summer, not for temperature, but for secrecy. What happens inside these rooms will remain classified for decades. Captain Keiji Fukuda commands the design team. He has spent 18 months studying every battleship engagement of the First World War, cataloging hull breaches, analyzing flooding patterns, reconstructing the final hours of vessels that rolled and sank under sustained punishment. His conclusion, distilled into a specification document that survives in fragmentary form, establishes a number that will define everything about the ships his team builds: 20. That's the target. 20 torpedo hits before loss of fighting capability, not 20 hits before sinking. 20 hits before the ship can no longer shoot back. Fukuda's specification assumes the vessel will eventually go down, but only after absorbing more punishment than any enemy could reasonably deliver in a single engagement. The math behind this number comes from operational analysis. American carrier air groups of the 1930s could launch perhaps 40 torpedo bombers per strike. Accounting for losses to anti-aircraft fire, fighter interception, mechanical failures, and the simple difficulty of hitting a maneuvering target, Fukuda's team estimated that maybe 8 torpedoes would actually connect per wave. A ship that could survive 20 hits could therefore absorb 2 full American carrier strikes and still fight. By the time a third strike arrived, the battle would be decided one way or another. The specification was not optimistic. A post-war assessment by the U.S. Strategic Bombing Survey noted. It was calculated. Fukuda's team approached the problem the way engineers approach any constraint. You work backward from the requirement. 20 torpedoes means a certain volume of flooding. That flooding demands a certain buoyancy reserve. That reserve requires a certain hull displacement. Run the numbers honestly, and you arrive at a ship that cannot weigh less than 65,000 tons standard displacement. Nothing that size had ever floated. The Washington Naval Treaty of 1922 had capped battleship displacement at 35,000 tons. Japan withdrew from that treaty in 1936, but the constraint had shaped a generation of naval architecture. Every designer in the world thought in 35,000-ton terms. Fukuda's team had to unlearn everything and start from displacement figures that made their colleagues uncomfortable. They started with the torpedo protection system. Traditional battleships used a single-layered defense, an outer hull, a void space, sometimes a torpedo bulkhead, then the inner hull. Fukuda demanded 5 layers. The outermost hull would absorb the initial blast. Behind it, a compartment filled with seawater would dissipate the shock wave. Behind that, an air-filled void to prevent hydraulic transmission of force. Behind that, another liquid-filled space. Behind that, a final armored bulkhead protecting the machinery spaces. Each layer added weight and width to the beam. The torpedo defense system alone required the hull to be nearly 40 meters wide, broader than any battleship afloat. Then came the armor. 16 inches on the main belt, 26 inches on the main turret faces, 9 inches on the deck to defeat plunging fire from long-range gunnery. The armor weight alone exceeded the total displacement of many heavy cruisers. The power plant needed to move this mass at 27 knots required 12 boilers and 4 turbines, generating 150,000 shaft horsepower. The fuel bunkers to feed those boilers on a Pacific crossing demanded 6,000 tons of oil capacity. Add it together, and you get Yamato. 72,000 tons fully loaded, 863 feet long. The largest, heaviest, most heavily armored warship ever constructed by any nation. The construction itself pushed Japanese industrial capacity to its limits. The slipway at Kura had to be deepened and widened. A special gantry crane, the largest in Asia, was built specifically to lift Yamato's turrets into place. Security was absolute. Workers traveled to the yard in covered trucks. Photographs were forbidden. The completed hull was draped in camouflage netting to hide its true dimensions from aerial observation. Japan built Yamato in secret because Japan understood what Yamato meant. This ship represented a strategic bet, the concentration of resources that might otherwise have built 3 conventional battleships into a single vessel that could theoretically defeat all 3. The gamble made sense if Fukuda's math held. 20 torpedoes, 2 carrier strikes absorbed, 1 ship holding the line for an entire fleet. What Fukuda's team could not calculate was what would happen if America simply refused to stop at 2 strikes. The assumption underlying Yamato's design was that battles end, fuel runs out, ammunition depletes, pilots exhaust themselves, carriers withdraw to rearm. Some natural limit constrains the violence that any single engagement can deliver. By October 1944, that assumption had collided with American industrial output. The U.S. Navy did not send 2 carriers against Musashi. It sent 5. The strikes did not come in waves with long pauses for rearming. They came continuously, overlapping, one air group attacking, while another was already inbound. Fukuda had designed for 20 torpedoes, delivered across an engagement that might last hours, with significant gaps. Musashi took 19 torpedoes in roughly 5 hours of near-continuous assault, plus 17 confirmed bomb hits that the specification had never adequately accounted for. The ship performed almost exactly as designed, and it still sank. Contact: battleships, heavy cruisers, destroyers, bearing 270, distance approximately 50 miles west of Tablas Strait. Lieutenant Junior Grade Max Adams transmits that sighting report at 8:12 in the morning, flying a Curtiss Helldiver off the carrier Intrepid. His radio crackles with static from the humid air over the Philippine archipelago. Below him, visible through scattered clouds, a Japanese fleet steams in formation towards San Bernardino Strait. Adams counts ships, 5 battleships, at least 10 heavy cruisers, destroyers screening in a wide arc. This is not a raiding force or a diversionary group. This is a battle fleet moving with purpose toward the American landing beaches at Leyte Gulf. The transmission reaches Admiral William Halsey aboard the battleship New Jersey 90 seconds later. Halsey has been waiting for this. The entire Third Fleet has been waiting for this. The chance to catch Japanese capital ships in open water before they can threaten the invasion transports. His staff had war-gamed this scenario for months. Search planes find the enemy. Carriers launch, battleships die. The question is not whether to attack. The question is, with how much? Halsey's answer arrives in the form of orders transmitted across the fleet within minutes of Adams' sighting report. Every available strike aircraft from Task Force 38, the fast carrier task force that forms Third Fleet's offensive punch, will concentrate against the Japanese formation, not a partial strike or a probing attack to assess enemy strength. Everything. Commander David McCampbell, leading Air Group 15 off the carrier Essex, receives the order while his Hellcat fighters are still warming on the flight deck. McCampbell has 23 confirmed kills to his name and will finish the war as the Navy's leading ace. He knows what a full fleet strike looks like. He also knows what happens when you throw every plane at a single target. "We're going to sink them all," his wing leader says over the radio. McCampbell does not correct him. The first strike launches at 9:10. 159 aircraft from 3 carriers, Intrepid, Cabot, and Independence, Helldivers carrying 1,000-pound bombs, and Avengers carrying Mark 13 torpedoes. Hellcats rode escort with rockets and machine guns. The formation climbs to 12,000 feet and turns west toward the Sibuyan Sea. Vice Admiral Takeo Kurita stands on the bridge of his flagship Yamato and watches them come. Kurita has commanded surface forces for 30 years. He fought at Java Sea and Midway and the Philippine Sea. He understands what carrier aircraft can do to ships without air cover. He watched Musashi's sister take bomb hits at the Battle of the Philippine Sea just 4 months earlier. His orders are to transit the Sibuyan Sea, pass through San Bernardino Strait at night, and fall on the American transports at dawn. The math is simple. He needs to survive approximately 8 hours of daylight transit. His fleet has no combat air patrol. Land-based aircraft from Philippine airfields were supposed to provide cover, but those airfields are burning. American strikes have systematically destroyed Japanese air power across Luzon over the previous 3 days. Kurita's fleet is naked. The first wave arrives at 10:26. Avengers drop to attack altitude, 200 feet, skimming the wave tops, throttles firewalled. The Japanese formation erupts in anti-aircraft fire. Every ship that can bring guns to bear opens up simultaneously. Tracers fill the air in overlapping cones of steel. Lieutenant Commander Ellis Blaine pushes his Avenger through the barrage, pickles his torpedo at 800 yards, and pulls up hard into a climbing turn that costs him his port aileron to a 25-millimeter burst. His torpedo runs true. It strikes Musashi amidships, port side, at 10:27. First blood. The Japanese gunners are not incompetent. They are not poorly trained. The problem is volume. Too many aircraft attacking from too many vectors for any anti-aircraft system to cover. American doctrine calls for splitting the strike into multiple approach corridors, forcing defenders to divide their fire. It works. 3 more torpedoes hit Musashi before the first wave withdraws. A bomb penetrates her forward deck and starts a fire in a damage control equipment compartment. Another bomb misses the ship, but detonates close enough to buckle plating near the bow. Kurita watches from Yamato, 3,000 yards astern. Musashi is listing slightly to port. Nothing serious. The ship is still making 25 knots and firing, still very much in the fight. The first wave withdraws at 10:55. Kurita's staff begins damage assessment. 4 torpedo hits on Musashi. 1 torpedo hit on the heavy cruiser Myoko, serious enough to force her retirement toward Brunei. Bomb damage across several ships, casualties in the hundreds. Kurita orders the fleet to continue toward San Bernardino Strait. He does not know that the second American strike is already inbound, or that a third will follow the second, or that Halsey has committed so many aircraft to this attack that his carriers will need to conduct emergency rearming cycles to sustain the tempo. The gap between Fukuda's design assumptions and American industrial reality is about to become visible. At 11:43, radar operators on Musashi detect the second wave, 173 aircraft this time, more than the first strike. They are coming from the east, flying in formations so dense that the radar returns blur together into a single massive contact. Lieutenant Commander Endo, in his damage control station, has just finished pumping out compartment C-115. He will not have time to finish the next one. The smell hits first. Fuel oil mixing with seawater creates a film that coats everything. Bulkheads, deck plates, the faces of men working in compartments, lit only by battle lanterns. The main lighting circuits failed after the 6th torpedo. Emergency power keeps the pumps running and the damage control phones connected, but visibility in the lower decks has collapsed to whatever a handheld lamp can illuminate. Petty Officer First Class Yoshida Masaharu leads a repair party through a passage ankle-deep in water that should not be there. His orders are to shore up a bulkhead in compartment B-23, a space that took stress from a near-miss bomb detonation 2 hours ago. The bulkhead is holding, but the frames behind it have buckled, and water is seeping through rivets that were tight yesterday. This is damage control as practiced on a ship being slowly murdered. You don't fix problems. You slow them down. Shored bulkheads buy time. Pumped compartments reduce list. The math is simple in theory. Water out faster than water in, and you survive. Yoshida's party carries lumber cut to standard lengths, wedges, hammers, and a portable pump that weighs 80 pounds. They have done this work 6 times since morning. The routine has become mechanical. Wedge, shore, pump, move to the next space. Nobody talks about winning anymore. They talk about stabilizing. We worked in absolute darkness at times. A damage control officer's post-war account recorded. You learned to feel the ship's angle through your feet. When the list changed, you knew before anyone told you. The counter-flooding system that Captain Fukuda designed a decade ago operates on a principle that seems elegant until you watch it fail. Every compartment has a twin on the opposite side of the ship. Flood one, you flood the other to balance. The ship rides lower in the water, but stays upright. Simple. The problem is that torpedoes do not distribute themselves evenly. By 1 p.m., Musashi has taken 11 torpedoes, 8 to port, 3 to starboard. The counter-flooding calculations that worked at 4 hits have become increasingly desperate at 11. To balance the port-side flooding, damage control has intentionally flooded starboard compartments that were never hit. The ship now carries thousands of tons of water that exist solely to offset other water. This irritates me more than it should. The designers built a system that fights damage by creating more damage. The logic is sound. A level ship survives longer than a listing one. But there's something perverse about a vessel that defends itself by drowning compartments that enemy weapons never touched. The men in those spaces had to evacuate before their own damage control teams opened the valves. Anyway, Lieutenant Commander Endo monitors the flooding from a station that now sits at a 12-degree angle, despite everything the counter-flooding system has done. His board shows green lights for compartments that are dry, yellow for those taking water, red for those fully flooded. The board looked mostly green at 10 a.m. By 1 p.m., yellow dominates the lower sections, and red is spreading upward. He has a telephone circuit to the bridge. Captain Toshihira Inoguchi calls every 15 minutes for status updates. The conversations follow a pattern. Can you correct the list? Working on it. How long? 30 minutes. The answer stopped being true an hour ago. Endo knows it. Inoguchi probably knows it too. But the question keeps coming, and the answer stays the same, because nobody has figured out what else to say. The second American strike has added 4 more torpedoes to the total. One of them hit a section that had already taken stress from an earlier impact. The hull plating there tore instead of flexing, and water poured through a hole larger than any the damage control manual anticipated. Standard doctrine assumes localized breaches that can be isolated. This breach spans the boundary between 2 compartments. Water does not respect blueprints. It flows toward the lowest available space, and when that space connects to another space, it flows there too. Endo watches his gauges track flooding that spreads faster than his teams can respond. At 1:44, the 13th torpedo strikes. Musashi shudders differently this time. The previous hits felt like punches, sharp, localized, followed by the groan of stressed metal. This one feels like the whole ship shifting on her keel. Something structural has changed. Endo's inclinometer shows the list increasing from 12 degrees to 15 in less than 2 minutes. His counter-flooding board shows he has already used every available starboard compartment. There is nothing left to flood. The mathematics of survival have stopped working. On the bridge, Captain Inoguchi receives Endo's report and does not respond immediately. The silence on the phone line stretches long enough that Endo wonders if the connection has failed. Then Inoguchi speaks. Continue damage control efforts. We will maintain course. The order makes sense tactically. Kurita needs every ship he can bring through San Bernardino Strait. A crippled Musashi is still better than no Musashi. The 18-inch guns can still fire. The engines are still running, reduced to 18 knots now, but running. What the order does not account for is the fourth American strike, already forming over the carriers 40 miles east. 100 aircraft this time. The air group commanders have received new targeting instructions. Concentrate on the cripple. Musashi has 3 hours left to live. Her damage control teams will spend those hours in flooded passageways, shoring bulkheads against water pressure that keeps increasing, pumping compartments that fill faster than the pumps can empty. They will do everything right. The ship is dying. We all know it now. Seaman Hosoda Kiyoshi writes those words in a pocket notebook at 2:15 in the afternoon. He is stationed at an ammunition hoist for the port side secondary battery, a position that has become irrelevant because the guns above him can no longer depress far enough to engage aircraft. The list has tilted the entire weapon system toward the sky. Hosoda's notebook survives because he survives. He will be one of approximately 1,300 men pulled from the water after Musashi goes down. His account, recorded in 1946 by American intelligence officers, provides one of the few enlisted perspectives on the ship's final hours. The fourth American strike arrives at 2:20. 75 aircraft from the carriers Lexington and Enterprise. The pilots have been briefed specifically on Musashi's condition. The listing hull visible from altitude, the reduced speed that makes torpedo runs easier, the anti-aircraft fire that has grown ragged as damage accumulates. They know they are finishing a kill. Watch what happens to the attack geometry. A healthy ship maneuvering at 27 knots presents a difficult torpedo target. The aircraft must lead the ship, estimate its turn, time the drop, miss by 50 yards, and the torpedo passes harmlessly astern. Musashi at 2:20 is making 12 knots and cannot turn sharply without risking a capsize. The lead calculations become trivial. The missed distance shrinks to almost nothing. 5 torpedoes hit in 11 minutes. All 5 strike the port side, the side already hammered by previous attacks, the side where the hull plating has been stressed and weakened, and in some places torn completely open. The cumulative effect is not 5 separate floods. It is the catastrophic failure of an entire section of the ship's watertight integrity. Lieutenant Commander Endo's damage control board goes dark. Not metaphorically. The electrical circuits feeding his station short out as water reaches junction boxes that were supposed to stay dry. He loses communication with 4 repair parties simultaneously. His last reading showed a list of 22 degrees. The smell changes. Seawater and fuel oil have dominated for hours, but now there is something else. The acrid bite of burning insulation, the metallic tang of superheated electrical components shorting out in flooded spaces. Somewhere below, a fire has started in a compartment that damage control cannot reach. Captain Inoguchi orders the crew to shift weight. Anything movable goes to the starboard side. Ammunition, stores, even the bodies of the dead. Men form human chains to pass shells from port magazines to starboard passageways. It is desperate improvisation, the kind of measure you attempt when doctrine has failed and physics is winning. The weight shift buys perhaps 2 degrees of correction. The ship is still listing 20 degrees to port. At 3:10, the fifth and final strike arrives. 67 aircraft. They find Musashi nearly stationary. The engines have stopped, either from flooding in the machinery spaces or from a deliberate decision to reduce the forces on the hull. The ship drifts in the Sibuyan Sea, her bow noticeably lower than her stern, her port rail nearly touching the waves. The attack takes 9 minutes, 4 more torpedoes, 2 more bombs. The numbers have stopped mattering. Musashi is no longer absorbing damage. She is collapsing under it. Hosoda feels the deck shift beneath his feet. Not the sharp lurch of a torpedo impact, but a slow, grinding rotation. The list is increasing continuously now, a degree every few minutes, gravity pulling the flooded port side down and the empty starboard side up. I could see the waterline rising on the port bulkhead, his account states. The paint was different colors at different heights, darker below the normal waterline, lighter above. I watched the dark paint disappear underwater. Then the light paint. Then the first row of rivets. At 3:20, Captain Inoguchi gives the order to abandon ship. The announcement reaches different parts of the vessel at different times. Some compartments still have working speakers. Others rely on runners, who may or may not survive the journey. Men begin climbing toward the starboard rail, which is now the highest point on a ship, tilted 30 degrees from vertical. Hosoda describes the sound. Metal groaning under stresses it was never designed to bear. Loose equipment sliding across decks and crashing into bulkheads. The deep, resonant boom of compartments imploding as they flood. Air pressure spiking and then releasing as water forces its way through failing seals. And underneath it all, the hiss of the sea entering the ship through wounds too numerous to count. Musashi rolls at 3:35. The capsizing takes less than a minute. Hosoda is in the water by then, swimming away from the suction he has been trained to fear. He turns back in time to see the hull, that massive armored hull that was supposed to survive 20 torpedoes, rise out of the water like a breaching whale. The red bottom paint catches the afternoon sun. The propellers, 4 of them, each nearly 20 feet across, spin slowly in the air. Then the stern rises higher, the bow dips, and Musashi slides beneath the surface. She has taken 19 torpedoes and 17 bombs. She has absorbed more punishment than any warship in history. Her damage control teams have performed exactly as trained, shoring and counter-flooding and pumping for 5 hours of continuous assault. The design worked, Fukuda's math held, and she still sank. Because American industrial capacity did not care about Japanese engineering. It simply kept sending aircraft until the engineering broke. How many torpedoes did Fukuda's team predict Musashi could survive? The design specifications from 1934 sit in Japanese naval archives, declassified after the war, translated by American intelligence officers, analyzed by engineers who wanted to understand what they had just sunk. The documents are technical and dry, full of stress calculations and flooding diagrams and probability curves. Buried in the mathematics is a number, 20 torpedo hits, distributed across both sides of the hull with functional damage control at design specifications. Musashi took 19. The ship performed almost exactly as her architects had calculated. The margin was a single torpedo, one more hit on the starboard side to balance the flooding, one more compartment to absorb, and the counter-flooding system might have held long enough for nightfall. Fukuda's drawings from a decade earlier predicted a vessel that could absorb catastrophic damage and remain afloat. That is precisely what happened for 5 hours and 9 minutes in the Sibuyan Sea. The design was vindicated. A post-war Japanese naval engineering review concluded. The ship exceeded combat survivability requirements for her class. The failure was not structural. Look at what that sentence does not say. It avoids claiming the ship survived or that the design succeeded. It says only that requirements were met, as if meeting requirements matters when your vessel is sitting on the bottom of the Philippine Sea. This is the gap that Japanese strategic planning never closed. They built the most survivable battleship in history and sent her into a battle where survivability was irrelevant. The Americans did not need to sink Musashi with a single strike or penetrate her armor with a single bomb. They needed only to keep attacking until the cumulative damage exceeded the cumulative capacity to resist it. 19 torpedoes, 17 bombs, 259 aircraft sorties against a single target in a single day. The numbers reveal something about American industrial philosophy that Japanese planners understood intellectually but could not counter practically. American doctrine did not assume individual weapons would be decisive. It assumed volume would be. Build enough torpedoes, train enough pilots, launch enough strikes, and eventually the target stops existing. The question is not whether you can sink a battleship. The question is how many aircraft you are willing to spend doing it. Halsey spent 259 sorties and lost 18 aircraft. The exchange rate was approximately 14 sorties per torpedo hit, 3 aircraft lost per battleship killed. Those numbers made sense to American war planners. They made no sense at all to Japanese architects who had spent a decade perfecting a hull that could survive 20 hits. The irony cuts deeper than simple miscalculation. Fukuda and his team were not wrong. Their stress models held. Their flooding predictions proved accurate. Their counter-flooding system worked exactly as designed until the damage exceeded its capacity. Every technical assumption in those 1934 blueprints was validated by the manner of Musashi's death. They just asked the wrong question. The question was never, how much damage can one ship absorb? The question was, how much damage can the enemy deliver? Japanese naval planning spent 15 years optimizing the first variable while ignoring the second. American industrial planning spent the same 15 years maximizing delivery capacity without particularly caring about individual ship survivability. The USS Yorktown sank at Midway after 3 bomb hits and 2 torpedoes. American planners shrugged and built more carriers. The IJN lost Musashi after absorbing 6 times that punishment. There was no replacement coming. The production numbers make this concrete. In 1944, American shipyards launched 7 fleet carriers and 9 light carriers. Japan launched none. American factories produced nearly 14,000 naval aircraft. Japan produced roughly 8,000, and fuel shortages grounded half of them. The capacity gap was not a matter of percentages. It was a matter of categories. Musashi could have survived 30 torpedoes, 50. It would not have mattered. The Americans would simply have launched more strikes. This is what the Japanese design philosophy could never escape: the assumption that quality could substitute for quantity, that a sufficiently advanced weapon system could offset industrial disadvantage. It was not a stupid assumption. Outnumbered forces have won battles throughout history by concentrating superior capabilities at decisive points, but concentration requires the enemy to cooperate by presenting those decisive points. The Americans refused to cooperate. They attacked everywhere, all the time, with more aircraft than Japanese gunners could track and more torpedoes than Japanese compartments could absorb. They turned the entire Pacific into a war of attrition and then won the attrition. The survivors pulled from the water after Musashi sank, 1,376 men out of a crew of 2,399 were interrogated over the following months. American intelligence officers asked detailed questions about damage control procedures, flooding sequences, the performance of specific systems. They were reverse engineering the sinking, learning what had worked and what had failed. The reports show grudging professional respect. Musashi's damage control was described as excellent. Her crew's discipline under sustained attack was noted as superior to expectations. The ship had done everything her designers intended. None of it had been enough. That is the lesson the Sibuyan Sea teaches, and it is not a comfortable one for anyone who believes in the power of engineering over economics. You can build the perfect warship. You can armor it against every threat you anticipate. You can train its crew to respond flawlessly under fire, and the enemy can still kill it by simply refusing to stop shooting. 3:35 p.m., October 24th, 1944. The Sibuyan Sea coordinates 13 degrees north, 122 degrees east. Musashi's hull settles on the seafloor at approximately 4,300 feet, deeper than any salvage technology of the era can reach, deeper than any diving bell can descend. The ship that took a decade to design and 4 years to build disappears in less than 60 seconds. Admiral Halsey receives confirmation of the sinking at 4:12. His staff logs the kill as 1 battleship destroyed, 18 aircraft lost. The exchange ratio satisfies Third Fleet's operational calculus. Task Force 38's air groups have expended roughly 11% of their available torpedo inventory and less than 2% of their total aircraft strength. They can sustain this rate of attrition indefinitely. The Japanese cannot. The next morning, American aircraft find the rest of Kurita's force emerging from San Bernardino Strait. They sink 3 more ships before noon. The production differential that built Musashi, those 15 years of concentrated naval engineering, proves irrelevant against an enemy who measures success in sorties per day rather than armor thickness per inch. We could see the industrial power, a captured Japanese staff officer told American interrogators in 1945. We could count the aircraft. We knew the production numbers, but knowing is not the same as understanding. We designed ships to survive battles. You designed a system to win wars. The distinction matters. Musashi represented the pinnacle of a philosophy that treated warships as chess pieces, valuable, irreplaceable, requiring preservation. American carrier doctrine treated aircraft as ammunition, expendable, replaceable, requiring only that the expenditure produce results. The Japanese built 1 Musashi. The Americans built the capacity to sink a Musashi every week if necessary. The capacity changed what naval warfare meant. Before October 1944, battleship armor remained a meaningful variable in tactical planning. Admirals calculated engagement ranges based on armor penetration curves. Naval architects obsessed over belt thickness and deck protection and torpedo defense depths. The assumption underlying all of it was that sufficient armor could render a ship functionally invulnerable to any practical attack. Musashi's sinking invalidated that assumption permanently. American weapons were not individually superior. The Mark 13 torpedo that killed Musashi was in many ways inferior to the Japanese Long Lance. American pilots were not better trained. The replacement aircrew of 1944 were adequate, not exceptional. Volume invalidated the assumption. 259 sorties generated enough hits to exhaust a damage control system designed to survive 20. The margin between design capacity and attack capacity was 39 torpedoes and bombs. The implications registered immediately. Within 6 months, the Imperial Japanese Navy abandoned offensive battleship operations entirely. Yamato, Musashi's sister ship, spent most of 1945 anchored at Kure, conserving fuel for a mission that would never come. When she finally sortied in April 1945, Operation Tengo, the one-way trip to Okinawa, American aircraft sank her in 2 hours. 12 torpedoes, 6 bombs. The attack was almost casual. The pilots knew what their predecessors had proven in the Sibuyan Sea. The clipboard that floated in Musashi's damage control station recorded 19 torpedo hits. The log represented the outer limit of what naval engineering could achieve against aerial assault in 1944. The number was impressive. The number was also irrelevant. American carrier groups could generate 19 torpedo hits before lunch and 19 more before dinner. The mathematics were never close. Seaman Hosoda Kiyoshi spent 11 hours in the water before a Japanese destroyer pulled him aboard. His notebook survived, waterlogged, the ink running on several pages, but legible. American intelligence officers photographed every page in 1946. The photographs sit in the National Archives now, filed under Japanese naval personnel, interrogation documents, Leyte Gulf operations. The final entry in the notebook is dated the day after the sinking. Hosoda wrote it aboard the destroyer that rescued him, wrapped in a blanket, drinking tea that someone had pressed into his hands. He did not write about the torpedoes, or the flooding, or the list that kept increasing until the ship rolled over. He did not write about the engineering or the damage control or the counter-flooding calculations that worked exactly as designed until they stopped working. He wrote about the sound. "I can still hear it," the entry reads. "The water coming in. It did not stop. We pumped and it came in. We shored and it came in. We flooded our own compartments and still it came in. 19 times they hit us. We survived 18. We almost survived 19. But the water kept coming. The water always kept coming." The water was American industrial capacity, translated into explosive ordnance. The sound was the noise a strategic miscalculation makes when it finally becomes undeniable. Hosoda heard it in the Sibuyan Sea. The Japanese naval staff recognized it in the after-action reports. For the engineers who designed Musashi, it echoed in the silence where replacement orders should have been. Hosoda's notebook does not record his thoughts about American production statistics or carrier doctrine or the strategic implications of volume-based warfare. It records the experience of a sailor who watched the most powerful warship ever built, absorb everything her designers intended her to absorb, and then sink anyway. "We did not lose to their weapons," he wrote. "We lost to their factories.